Hi, I'm Steve Ward and welcome to this session on programming and programming languages. Let's start by defining what is programming. Programming is the process of creating source code for a solution to a problem that will be implemented using a computer system. Programming is implemented using a programming language. This is also known as coding, with code being the output. The program code, once developed, is run on the computer by either using an interpreter or by compiling the program to run natively on the computer hardware. Programs may be standalone or, more likely today, developed in some sort of framework. Note the convention we're using here of American spelling of program as opposed to the British program with ME. This is just a convention of the computer industry that's been around for some time. However, both uses are correct. An interesting point is, if you're programming an automation system, then we have HMI SCADA, where you're often programming in a high-level language, but you also might be programming a programmable logic controller, or PLC. And as well as known as being coding, the code can also be referred to as logic. So code is the representation of the computer language. Lines of code make up the program. These lines include initializations and definitions. There's a start and end, so the code knows where to start and when to stop. There are control structures. There may be subroutines or functions. And then there's the actual code that's used to perform the required application itself. Now, source code is human readable, but compiled code is not. But there may also be intermediate code, which may or may not be human readable, although generally the intermediate code, if it is human readable, would be to a lesser extent than the original source code. Now, one benefit of this is, if you are compiling a program, the source code remains behind, so from an intellectual property point of view, compiling an application is worthwhile, and also intermediate code that's not human readable, that's also worthwhile because you can preserve your intellectual property in the source code and then distribute the compiled code or intermediate code for the user to run, and then they can't steal your intellectual property. Here's a list of popular programming languages. Python is probably the most popular programming language at the time of developing this slide deck. It's easy to develop and understand, and there are lots of libraries available. It's not the most efficient though. Another very popular language is C, these days pretty much superseded by C++. C is the original language. C++ is a more enhanced version which has more object orientation, and I'll talk a bit more about that later. So C is a traditional high-performance language, but I would say it's not as readable as Python and not as easy to use. However, it does run closer to the hardware, and also it's often compiled, whereas Python isn't so much. Now, other languages which are a combination of different styles include Java. Java was originally developed as a platform-independent language, and the idea is it runs on any platform for which there is a Java runtime. Because it's running in this intermediate code using the Java runtime, that does mean that performance is reduced. I originally started programming Java many years ago, and at the time Java was very slow. But over the years, computer platforms have got faster, and also the runtimes have got more and more optimized. So modern performance isn't so much defined by the language, it's often defined by the computer platform itself and whatever sort of interpreted or intermediate type platform you're running on. But a compiled program generally will always be faster. Now, Java was open source, so Microsoft developed C#. This is based loosely on Java, but it has diverged over the years. Originally it was very close to Java, but now it's quite a bit different. Now, another language here is called JavaScript. JavaScript is an embedded version of Java that doesn't include all of the object-oriented type functions that Java supports. JavaScript is often found in web pages, and those JavaScripts can be huge. You might download a file that's several 100,000 bytes, and a lot of that might be code, and typically that code, if you're downloading the website, would be JavaScript. For example, if you're using Salesforce, or if you're using the online versions of, say, Office, all of those applications are running huge Java applications natively inside your browser. Now, a very old language is called BASIC, which stands for Beginner's All Symbolic Instruction Code. This is a very old language. It's one I first used to write a long time ago. And the benefit of BASIC is it's relatively simple to use. Later, Microsoft did embed BASIC as Visual Basic for applications inside Office. So Excel, Word, Access, PowerPoint, but to a lesser extent maybe. They do include the option of having some automation using VBA. And some Microsoft applications also use another version of BASIC called VB.NET. So the .NET framework supports a version of Visual Basic. BASIC itself, it's often frowned upon. The very old versions used line numbers, which meant that program flow and logic was very complicated because there were lots of jumps and go-tos. Modern versions are better, but BASIC's often frowned upon, and these days I would say it's overtaken by Python as the most popular and easier to use language. Now we also have SQL or SQL, which stands for Structured Query Language. This is used for querying databases, and I won't go into any more detail on databases because they're a subject in their own right. I have got another session that covers databases in more detail. And the last one here is Assembler. Assembler uses native CPU processor functions for direct execution on the CPU. This makes them very difficult to program, but they are very fast and efficient. So if you look at that in terms of performance, C is quite performant due to its being compiled. But if you were writing assembler, C effectively compiles into assembler. If you start with assembler, then you can write some very fast applications. However, high-level functions might be very difficult, and it depends on the instruction set of the CPU as to how easy or difficult it is. But generally, very few people program in assembler these days, unless it's a very simple application, maybe a device driver, maybe you've got like an embedded application with a simple CPU. But most of the time, people aren't using assembler anymore. Let's talk a bit more about compiled code versus interpreted code. Compiling takes the original so-called high-level code, which is the code that the user writes, and converts it into machine code that can be run directly on the computer's CPU. So as I said on the previous slide, what this generally means is if you have, for example, a C program, when you run the compilation, that converts it into assembly code that's run directly on the hardware. So sometimes we call this about running on bare metal. The benefit is it's very fast because you're using those native CPU instructions, which are effectively the fastest you can go. However, you do need to run the compilation step. What you also need to do is every time you have a new platform, you potentially need to recompile the code for every platform that you'll run on. So that may not be the case for if you're consistently using Intel, but even then, compiling different versions may help with different generations of Intel CPUs, which have slightly different instruction sets. But certainly if you went from, say, Intel with x86, if you went to an ARM type CPU, you would definitely have to recompile because the underlying assembler is different. Now there's another issue with compilation as well. When you're compiling a program, you can often detect syntax errors, but you don't necessarily detect runtime errors. Runtime errors, they often only occur when the application runs. So there's a lot of work you need to do there to detect what might go wrong when the application runs. Now the alternative to compiling is an interpreter. This is a program or an application by itself that takes each line of the code and executes it one by one. This allows the code to be written once and run on multiple platforms, provided that you've got that interpreter for each platform. Now, the downside is it's a bit slower because when you're doing the interpreting, you have to execute each line one by one every time you run the code. You've still got the possibility of syntax errors, but interpreting can run through the program before it's executed, and that can detect some potential runtime errors before they occur. So you have got maybe better error detection here, although that depends on how effective your interpreter is. But the key benefit of interpretation is that you can write that interpreter, the executing program that runs that code, you can write that on multiple platforms and you don't need to recompile each platform it will run on. And it depends how often you're writing your programs. If you're writing for, say, successive versions of the Intel CPUs, you might find you need to recompile every few years if you want to use new architectures. For example, we went from x86, which is 32-bit, to x64, and that needs recompiling. But also each successive CPU has additional instructions, and in order to be the most effective, you might want to recompile to take advantage of those instructions, which are new on each platform, which is for Intel once every year. Another factor is that the compilers are often optimizing compilers, and each successive version of the compiler itself can produce code that's more performant just by the nature of the compiler itself can be better optimizing from each generation of compiler to the next compiler. So the thing is, these days it is confusing, since many applications are pre-compiled into an intermediate language that is run by an interpreter. This gives you a benefit of the both. And for example, your browser is effectively like an application like that running JavaScript. So JavaScript is sort of pre-compiled, although it's often run purely as text. But if you've got other applications like Java, that's pre-compiled. Python is sort of pre-compiled as well, or interpreted. So there's a big crossover between these two terms now, and it's much harder to point at a single application and say, yeah, that's definitely interpreter, or that's definitely a compiled application. And in big applications, you often mix the two anyway. But the key point there is if you pre-compile into this intermediate language that's run by the interpreter, the intermediate language gives you an performance improvement over a pure interpreted language. But again, it gives you that ability to run on multiple platforms without recompiling. So that was the aim of Java. You had your Java runtime, which is compiled for multiple platforms. But your original Java, not JavaScript, this is Java, your original Java compiles into a P code, which is like an intermediate code, and then it's that P code which is executed on each system. Now Java, as I said, Java started off very slow, but over the years the computer platforms have got faster, but also those applications that run the P code, they've become optimized and got faster as well. So the Java runtime is getting successively faster. The same with, we mentioned before, VB.NET. So VB.NET is running on top of the .NET framework, and every year or so Microsoft improves the performance of .NET. And of course, if you're updating your computer every few years, you'll get benefits of improvement from that. So it's very hard to point at a single thing and say, this is good or this is bad. You have to look at everything from a system level to say which is the best and which is the worst. So no implied criticism of compiled versus interpreted code here. They both have their uses. But I would say, of course, if you are writing a very high-speed application, then ultimately it will need to be compiled down to assembler code. And then you have the issues of maintaining that. And we'll talk about that in later slides. Now, here's an example of why Python is so simple to use. If you want to have the very simplest program, we've got the so-called Hello World application. And this is often how people start, by understanding the syntax of a program. So for Python, you do print, open brackets, inside the brackets you have inverted commas to specify its text, and then you enter your text, hello world. When you run that program using your Python execution environment, that would print out hello world to your standard terminal, which is typically your screen or your interpreting window that you're running. If you want to do maths, that's pretty straightforward as well. You can assign a value to a variable. So we're saying value equals 5. That assigns the value of 5 to the variable called value. And then what we do is we print again, and now we're using a format function. And then inside the curly brackets there we've got value. So that prints the original value of the value variable multiplied by 2. That would be printed up onto your screen. And then again we've got curly brackets where we've got an embedded instruction, value times 2. So we've got some very simple examples here, just in 1 or 2 lines, that show how easy it is to construct that application. You don't need any more than that. Whereas if you were using some other functions, you'd have to do a definition of value before you did anything. You might need to include the system resources which allow you to print. And to be fair, Python might make you do that as well, but generally you don't. You might also need to do things like specifying the start and the end of the program. So more traditional programs might need a lot more syntax around that before you even get started. But with Python, you can have a legitimate one-line program that does something useful. Now, programs don't exist in isolation. We often start with a platform. So the platform is the environment in which that code will run. So that could include the underlying hardware in the operating system, although not always, because that might be taken as granted. Now, programming is often independent of the platform, but may be constrained by it. So for example, there may be applications which are compiled to run on one particular piece of hardware. That means they won't run on something else. And also, of course, performance, that may affect your programming. And it may be if you've got a very slow computer, it will not run your application fast enough to be useful. So again, you do have to think of things in terms of the overall system, not just of the application code itself. So a common computer platform these days would include Wintel, not referred to so much recently, but this is the combination of Windows operating system with an Intel x86 or x64 CPU. That also includes ARM CPUs, which are x86 and x64 compatible. And the other common platform is Linux. And there's a variety of different flavors of Linux, but arguably they're all very similar, although Linux purists might disagree with that. But then you've got a choice of possibly more operating systems and underlying computer platforms and CPUs. So you've got a variety of different Linux flavors. Again, x86 and x64 Intel CPUs. I would say that these days you don't see many x86 CPUs. Everything is x64 capable. But having said that, you can still have an x86 application that will run on an x64 CPU. But with Linux, you now also get the opportunity for running maybe a variety of different embedded CPUs, such as ARM, A53 and so on, which are much smaller system-on-chip type devices. And if you want to know more about these different platforms, I have got another session on computer hardware that would help you on that one. So we've got the common platform, which is either Windows and Linux running on top of these different CPU types. The Windows operating system and the Linux operating system, what they do is they provide services to the applications to interface between the application itself and the underlying hardware. So for example, to read and write the hard disk, to allow you to have operator input via the mouse or keyboard, to allow you to read and write out to a display and to a printer and so on. So those are the sorts of services we mean. And the idea of the operating system, it gives you a common set of services regardless of exactly what the underlying hardware looks like. Again, a bit of history there. I remember it used to be in the olden days, if you wanted to print from a program, you had to install a print driver which was written specifically for that computer application. More recently now with Windows itself would have the computer printer driver, and you wouldn't need multiple drivers for each application. You'd just need a driver for that printer for Windows, and then Windows provides those services to allow your application to print. So in theory, this idea of the operating system providing the services makes life a lot easier when you're writing these applications. Now, platforms can also be extended to include development frameworks and even databases. So for example, Microsoft.NET is a development framework that gives you a lot of common functions that make it easier to write applications. And Microsoft SQL Server, this is an example of a database that allows you to store data into a relational database management system in a structured way, and it simplifies the way the data is organized and the way the data is stored and the way the data is retrieved. So, platform can include a wider system, and arguably a platform could include a computer architecture including network computers, because it's quite possible to have a database running on a separate server or even in the cloud. So you're using a large variety of different computer technology as part of your overall platform. In industry, industrial platforms might also include the HMI SCADA, PLCs, and their associated development packages as well. So for example, when you program a PLC or you develop HMI SCADA, it will have a package that allows you to create the applications which run on those devices. And again, they may include other functions. So you might have a PLC programming software that uses SQL Server for data storage and runs on top of Microsoft.NET, itself running on top of Windows, itself running on top of an x64 CPU. So there's also this concept of layering as well. So again, that's something else to be considered. But these days, that's often taken for granted. It's particularly in the industrial applications, you're very much constrained by the vendor is exactly what's required and what's supported. But if you're developing your own applications, and particularly as time goes by, you can end up with a very complex set of development frameworks and databases, depending on on where you start and what technology you want to use. But the idea of this platform is, this is all of the components, both underlying hardware and software and the operating system that you use to run your code. Now the program itself has a structure and it has syntax. The idea is programming languages have strict rules to follow regarding both of these, the structure and the syntax. And the reason for this is if you use the wrong structure or syntax, then the computer can't understand what you're trying to get it to do and it will not compile or run. Or worse, sometimes it will run, but it won't do what you want it to do. So typical programming rules include start and end definitions, such as begin and end, or start and end. You might have end of line characters. So for example, some applications need a semicolon. There might be comparison operators, greater than, less than, equals, and so on. You might need to define variables before you use them. And if you define them, you might define them as a particular data type. And depending on the application you're using, that syntax and structure can be quite complicated. So if you're developing code, you must consult the relevant documentation to determine what the required structure and syntax is. And just to make it even harder, this structure and syntax often varies during the life of a programming software. So for example, if you move up from say Python version 2 to Python version 3, some things will continue to work unchanged, some things will need changes, and some things may need a lot of changes. If the old Python 2 function is deprecated in version 3, you'll have to completely rewrite that function to make it work. So it's not just a matter of writing a program once and it runs forever. Programs do need ongoing maintenance. Now, as I mentioned, if you've got the wrong structure or syntax, then the program will typically not compile. You'll get compilation errors. Or if it does compile, it may not run. So that structure or syntax, that's the definition of what the program looks like. But it's also possible that even if the program does run, it doesn't do what you want it to do. This is often known as a semantic error. Some errors, which we also refer to as bugs, they may only recur at runtime. So for example, you might have an application that opens on a file on the hard disk. That file might be missing. So the program has a runtime error. You can't test for this when you're compiling the program, although it might be possible in some development environments, but generally it's not. Another possibility is a variable goes out of range. So for example, if you've got an integer value that can hold a value between say 0 and 65,000, if you multiply two big numbers together, you might end up with a result which is bigger than 65,000 and you get an out of range error. And that might only occur at runtime when you actually read values from a file or when the user enters numbers. There might also be a network resource not available because the network is down. For example, we talked about SQL Server. There's also SQL Azure in the cloud. If you haven't got a network connection, you might not be able to access the SQL Server database because there's no connection. So that might be a runtime error. So whatever your application does, it needs to handle these errors as well as handle the normal working. So there's a lot goes into developing applications to make them robust and to make them able to handle errors and to degrade successfully and gracefully if anything does go wrong. I mentioned object orientation. Object-oriented programming, or OOP or OOP, is a modular programming paradigm based on the concept of objects which can contain data and code. The idea is what you do is you define your object as a class and then you instantiate that class as an object. So the object is like the high-level definition, and then you can have multiple instances of that object. So let's say, for example, you've got a database application. You might have an object which is person, and then the instantiated objects are the individual people themselves. So the definition might include name, first name, surname. It might include age, date of birth, and so on. So all of those are the definitions. And then an instantiation of an object might be someone like me, Steve Ward, and my age, my date of birth, and so on. And that would be the instantiated version of the object. What we do in many cases, we have data is in the form of fields, which are also known as attributes or properties. And in the code, what we do is we have procedures or methods. And the idea is you can execute a procedure or method, and then that will affect the data. And then to read the data, you read the attributes or properties of the object. And the idea of this is it allows us to take a complicated application and develop it by breaking it down into simpler objects that then can be tested independently and developed independently. And that also allows for easier maintenance in future, and it allows for splitting up into multiple teams. Each team can be given a definition of what their object-oriented function needs to do, and then they can write that, they can test it independently, and then you can assemble all of these objects together later into an application that will work as a single entity. And also, if you've got these objects, you can reuse those in future applications. Now, most languages now have some form of object-oriented programming capability. Very few which don't do that. Possibly JavaScript is one example. You have very limited object-oriented programming in that case, but certainly Java does. C, maybe not the original C, but C++ does. Python does. Whether you use this or not really depends on how complex your application is, but it's definitely a best practice for when you're developing larger and reusable applications. Maybe you wouldn't use this initially. There's a concept of like a minimum viable product where you might want to throw an application together to give the very basic functionality you need, just as like a proof of concept. But my advice would be once you've developed that minimum viable product, you should then go away and almost redevelop the whole thing from the start. Knowing what you've learned from the minimum viable product or the MVP, you can now develop your final application with a proper framework that will help you in future. And that's often where object orientation comes in later, because you don't know what objects you need until you've already started coding. So it's a bit of a chicken and egg sometimes. There are programming purists who say you develop your objects first, but you might not know what all the objects are and what you need until you've actually started developing the program. So MVP, minimum viable product, that might be where you don't use objects, but it would be a good idea to then come back and rewrite or refactor at least your code and then start using objects to make it easier to maintain in the future. Can also mean more modularity of your application as well. Maybe you're not using full objects, but by having reusable subroutines or functions, that can also help you in terms of being able to write maintainable, reusable code. Let's define data, data structures, and variables. Pretty much all applications, in fact every application really, they always act on data. It might be a simple value. So for example, in the hello world function we saw earlier, you could say hello world is the data and the function is to print it onto the screen. So even in that very simple one-line application, we've got some data. In the second one we saw where we assign a value of 5 to the variable value, again we've got a value there that we can then act on, and the code prints out the value and also the value times 2. So even in those very simple applications, we do have data that we act on. Now, in those applications we saw, those are simple values, but data can also include complex data structures. And that can go all the way from like the simple variables we saw, all the way up to a complete abstract representation of the real world. So for example, if you're referring to a person, you might have first name, middle names, last name, date of birth, age, where they live, where they were born. There's all those sorts of representations of real world values that we would represent inside that data. Now generally what we do inside the computer program is we represent data by variables and we manipulate using operators. And then what we can do with those operations, they can be returned to a variable and written to output devices. I guess another thing we could do is we could also do tests on operators or variables, and that could cause us to do different things within the application as well. So that's another thing we can do. We can do an operation, and then rather than return that to a variable, we could actually change the way the function works. So for example, if you were going to have some sort of application, you might do a test on the person's age, and if they're under 18 you do one thing, and if they're over 18 you do something else. So that would be another example. Another possibility might be you're looking at person's name and you might want to concatenate that into first and last name and ignore all their middle names. So again, that you might return the first name, last name into a new variable called full name. So there's a lot of different things you can do, but fundamentally it comes down to performing an operation and then writing that to a variable or writing it to an output device, all affecting the structure of your application. As I said, variables can be single values, they can be arrays of multiple values, or they can be structures. Arrays are important because that allows us to have lots of values together of the same type, but then you can reference the different values within that array by using an index. So for example, if you've got an array of full names, you might have me, you might have Bill Smith, you might have Mandy Murray, you might have a bunch of other names. And what you could do is you could index through the array to bring out an individual full name by specifying that element number. Normally we start with 0, sometimes we start with 1, but typically array, square bracket or open bracket, 0 close bracket or close square bracket, that would normally bring us the first element of the array. The second element would be array 1, the third element would be array 2, and so on. Structures are slightly different. Structures are where we can include different types of variables, and that can also include lists of values as well, even if they're not the same type. And we can also have complex structures, and if your structures get very complicated, then we're into the realms of an SQL database. But we can manipulate complex structures as well. We might want to sort through them, we might want to search, we might want to organize them, we might want to combine them. So there's lots of things we want to do, and of course all of this ultimately depends on what you're trying to achieve within your application. So I mentioned name, address. They might be examples of types of data we manipulate. We might also be looking at, in industrial terms, temperature or flows or pressures. We might be looking at a time that something occurs or that something is supposed to occur. We might be looking at dates, that also might be another type of time. In a higher level system, we might be looking at order numbers, or we might be looking at order histories. There's a big range of things we can do. So for example, if you ever order on well-known shopping sites, typically you'll get your order reference or order number, and the order history could include things like when the date the order was placed, when the order was invoiced, when it was shipped, and so on. So there's lots of different things there. Temperature and flows and pressures, they're pretty straightforward. And we already covered things like time and name and address, they're straightforward as well. But this data, it might be that any one data item itself might consist of multiple aspects. So temperature, if I told you the temperature was 20 degrees, if we're having a normal conversation, you might assume that that's the current temperature for today, and it might well be. But when you're looking at a computer record, you might want more around that to know exactly what that means. So you might want to associate a temperature with a time, so you know that when that batch started, for example, that the temperature was 20 degrees at 8 o'clock in the morning, for example. Depending how complex your application is, of course, temperature might also be affected by flow and pressure. So you might want to have something that combines all three of those values along with the time in order to make sense of it. Because the temperature might be 20 degrees, but if the pressure's low, then that could indicate that it's actually not that high. But if the pressure went up, then depending on what you're manipulating, the temperature might go up or down. So, and flow can also affect that as well. For example, if you stand outside when it's windy, it feels colder than if you're standing outside when it's not windy. There's a so-called air cooling effect or wind chill factor. So again, it might be that one item of data by itself, it needs additional data in order for it to have context. Another thing that data needs is a data type, and this also introduces into the concepts of typing. So data type is the type of value that a variable or the element of a structure can hold. So for example, when we talk about a name, typically that's a string. So it's a string of characters. Each character is typically either an ASCII. ASCII is an old American standards interchange format for alphanumeric values. These days we often might have a more complex one to cover international characters as well. If you're looking at numbers, again, you might have an integer value, so that can hold a number that is multiples of 1. So when I say the temperature is 20 degrees, if you're holding that in an integer value, the next temperature up would be 21, the next temperature down would be 19. You might also have floating point values. So in case of a floating point, you might say, well, it's 20 degrees, and then you could also record 20.1 or 20.05. So the idea of these different data types are very important to allow you to define what allowable data there is. And also when you're converting values and when you're doing these comparisons and so on, data types are important there because not all data can be compared with all other types of data. Now, different languages have different levels of data typing. Some languages are very loosely typed, but some are very strongly typed. So for example, with Python, you can define a variable just by assigning a value to it, and the type is determined by the value assigned, and that may change later depending on what sort of calculations you do. But for example, if you say value equals 5, then Python will assume that the value variable is going to be a number, and then that number can then be compared against other numbers. With C#, it's slightly different. Here you've got to declare the variable first. If you don't declare the variable and you type to define it, you'll get a compilation error and it will just say undefined variable. So you have to say define something like define value equals, or define value as integer, say, and then that will define that value is able to hold integer numbers. If you don't define it first, you won't be able to do that definition or first assignment. And then also, when you're declaring and comparing values, that declaration can define what sorts of things you can do against it. It is possible to convert from one type of variable to another, but that might not work. So for example, if I've got a string of my name, if I try that to convert to an integer, that would probably fail, because what integer do you use? Do you use the ASCII value of one of the characters, which might work? Do you try and parse the string to work out if it reads as a number? So if you had a string with the characters ELEVEN, that could be interpreted as 11, but maybe not. So it gets very complicated when you start comparing different types. So that's why you should really define your variable types before. But again, this might depend on standards you have. It will depend on the capabilities of the programming language you have, and it also, to some extent, it depends on your personal preference a bit as well. Here are some typical data types. Boolean or bit. This has two states. So because it's a single bit inside the computer, the value could be on or off. So that could represent 0 or 1, true or false. Maybe some other things which are only having two states. So, for example, are you working or not? That could be used to represent those two states, and you could use a Boolean or a bit to do that. Integer, or int for short. This is 16 bits, often with a sign bit. Not always, again you have to check your programming documentation, but typically with an integer it's a signed integer, so you have 15 bits representing the number, and that can represent a number between 0 and 32767 in the positive range, and 0 down to 32768 in the negative range. It's that top bit which defines whether it's a positive or negative. So the way that works is, you've got 15 bits for the number and 1 bit for the sign. You can also have real values or floating values. These are typically comprised of 32 bits or sometimes 64 bits for high precision real. And the idea now is you've got a number that's represented with a decimal point. So you'll have a mantissa and an exponent, and probably a sign bit as well. So this way the number's now split into 3 bits. The mantissa would be your actual number itself. The sign bit would be whether it's positive or negative, and the exponent would be like a power of 10 to say what the value is. Strings, we covered that. String is typically 1 or bytes used to hold characters. With a byte, that would be used for old style 8-bit or 7-bit characters. More likely these days we use 2 bytes because we want to use Unicode, which is the latest standard. Unicode gives us 65,000 different values, and that allows us to cover international languages, not just English. And then there might be specialized data types like date or time. So these allow you to store date and or sometimes only time values. And the formats and the underlying structures may vary. It might be an 8-byte number that stores the seconds since the 1st of January 1970. It might be the milliseconds since a particular time, maybe the start of the day. Or it might be BCD, binary coded decimal, or it might even be ASCII coded. So again, you need to check your documentation to understand how the data types are composed. And what might be important is how much data, how much memory does each data type take up. Often people use integer because it's efficient. You're only using 16 bits, which is 2 bytes or 1 word. Some people think that if you use a bit, that's efficient because you're only using 1 bit. But that's not always the case. Some applications, they have to use a whole byte for every bit because they don't have concepts of being able to address a single bit within a byte. And again, date or time, they can be either very simple, going down to as little as typically 8 bytes, but they may be a lot more. A string, that can be as long as the string is. And real or float, again, typically they're 32 bits or 4 bytes or 2 words, or they would be 64 bits, which is 8 bytes or 4 words. So again, when it comes down to memory storage, that can have an impact as well. But this is normally something that comes in afterwards. Normally you would want to write your program first. Again, there's that concept of that minimum viable product. Once your programming is working, then you can always go back and optimize it for better data types later. So we talked about operators. Operators are functions that can be performed on variables. So we can do comparisons, equals, not equals, less than or equal to, greater than or equal to. There are also mathematical operators. We can add and subtract, or plus or minus. We can multiply and divide. We can raise to the power of. But there are also other mathematical operators as well, like absolute, to ignore the sign bit and just take the positive value of the number we're looking at. Maybe if we're working on floating point values, we might be looking at sine, cosine, tangents, and so on. And there may be many others, depending on how advanced your application is and what types of functions you're trying to do. For strings, there are a variety of string operators. We might want to concatenate a string. We might want to determine the length of a string. We might want to split one string into 2 different strings based on the length, or possibly a character that's within that string. So for example, if you've got a string that's my name, you might want to split it into first name and last name, and you might be looking for a space in the middle. There are also logical operators in comparisons, and, or, not, exclusive, or, and so on. And the idea of these is, you can take 2 or more comparisons and you can combine those with 2 or more logical operators. So you might want to say, only do something if your first name is one thing and your age is greater than something else. So in that case, we're using the AND operator to combine the 2 comparisons and only perform the function if they are both true. There are also bitwise operators which use the same and, or, not, exclusive, and so on, but this time they can actually perform operations or actions on the variables, normally down to a binary level. So logical operators in comparisons and the bitwise operators, they use the same functions, but they operate at different levels. So with and, or, not, exclusive, or as bitwise operators, we're typically looking at the bits within 2 or more values, and we're comparing each bit against the corresponding other bit in the other value, and then we're performing a function that way. For example, we might have a word value, and if we want to mask off the bottom 8 bytes, we could do, the bottom 8 bits, we might do ANDing of the first variable with 255, or FF in hex, and the idea of that is that would AND, and where there's a 0 in the second operator, that would result as 0 in the output. Where there's a 1 in the second operator, then it would copy the original value. So good for masking upper and lower bytes and so on. Those are quite advanced, but when you're handling certain applications where you've got lots of bits and bytes which need operating on, then you definitely start to get involved in those. That can include communications, particularly for embedded type devices and industrial applications where people try and pack lots of data into a single word, and you may need to mask out individual bits or bytes from those words. Pointers are something that are often associated with older programming languages. And the idea of a pointer is, instead of using a variable, a pointer points to a memory area. So that the pointer is a reference to that location within physical memory. And then the application, instead of using the variables, it directly references the memory using that pointer. Now this is very complex because if you get your pointers incorrectly configured, you can end up overwriting data that you don't want to overwrite, or reading the wrong data that you didn't want to read. If you're not careful, and with some applications, you can even end up overwriting memory that's not associated with the memory itself. You might be overwriting parts of the application code, or even parts of the operating system, or parts of code that belong to other applications. So you've got to be very careful to define what the meaning of that memory is, and you've got to be very careful to manage your memory to avoid overwriting other data or code. Now, modern systems do prevent the application from writing outside of boundaries, but even then within a boundary, you might still be overwriting the wrong part. The benefit of pointers is pointers often work very well at a low level inside the actual CPU itself, because what you can do is you can feed a value to the CPU, and that CPU can use that value as an offset and read that memory directly from within its cache or from within the real memory. And that can mean that you can get very, very fast access to data without having to go through any sort of conversion process to convert the actual value into another value or to do whatever handling you need. So the benefit of pointers is very, very fast, can also be very efficient on memory usage, but equally very difficult to manage and potentially very dangerous if your environment doesn't prevent you writing outside of defined ranges. Now, some applications just run from start to end. Sometimes there might be a single loop where the program runs from the start to the end and then goes back to the start again. But what you normally find is in most applications, there is a program flow, and what you need to do is you need to implement program flow control to define what order the program actually executes in. It's very rare you have to do everything from start to finish. There will normally be some sort of decisions, there may be jumps, there may be loops, and then there may be other things you need to do. So decisions could include an if statement. So typically what you do is you would say if followed by your condition. If your condition is true, then you run the code after then. But there's also an else condition. If your decision or condition is not true in the if statement, then you run the code after else. You can also get case. Case is where you can say you have an input value, and you can say if the input value is 1, do this. If the input value is 2, do this. If the input value is 3, do this, and so on. So that's where you might have multiple results. And it makes the program more readable to use a case function rather than multiple if, then, else type functions. So decisions are very common because you might not want to do everything every time. Recursions and loops. This is common where maybe you want to loop through an array, or maybe you want to test a series of functions one after another, or maybe you want to delay. Whatever the reason is, you've got things like a for next loop. A for next loop typically runs a defined set of operations from a starting number to an ending number. But you can also get conditional loops like repeat until. So repeat does something and then until a condition is true or a condition is false. And you can also do while, again, which is similar. The difference is that generally repeat or do, depending on the syntax of the application, they will normally do something once or maybe not at all, depending on the structure of the application. So different ways of using that to do something at least once, or maybe you don't want it to execute at all, or maybe you want it to execute a certain number of times. So there's different recursion and loop functions for that. You can also have subroutines and functions. These are a way of optimizing your code. So for example, if you want to do something multiple times, you might define that as a subroutine or a function. Then instead of executing that individual code multiple times in your application, you define it once as a function and then execute that function or subroutine. So you define your subroutine or function once at the beginning of the program, and then whenever you use it, you can specify that subroutine or function, and your compiler or your interpreter will sort out to run that logic without you having to enter it multiple times. Again, minimum viable product, maybe that doesn't matter, but certainly as you modularize your program through your second loop and you want to optimize your code, it's a good idea to split out common subroutines and functions, because that can help readability of the application, can also make it easier to maintain, and also those subroutines and functions, you can take those and reuse them in future applications. So this is part of your object-oriented programming. Now there may be jumps. Modern applications don't tend to jump too much, but some older applications, particularly with BASIC, you had this concept of line numbers, and you could go to a line number to jump over a section of code or to jump backwards and implement a loop. So difficult to read, difficult to manage, but some applications do use those jumps. And the final one for program flow control is what happens if there's an error. So you can do some error handling logic. So for example, in BASIC, you've got the on the error go to, and you can jump to a line number or jump to a label if there is an error. With modern languages, you normally get something like a try and then an exception type basis, where you try and then you have all your code. And if there's anything goes wrong, then you run the code in the exception part. So that can include error handling to tell the operator what went wrong, or maybe try and recover, or maybe abort gracefully, or maybe whatever. Again, depends on what your application is trying to do. But error handling could be very important. Again, maybe for the MVP you don't do much of that, but certainly as your application evolves, you want to get more and more sophisticated error handling. Now, I'm going to emphasize error handling. It's often neglected. Errors can result from multiple issues. It might be poor programming in the first place. It might be resource issues like not enough memory, or something is not available, like we said, that that remote database or the network. It might be poor quality inputs because your inputs aren't sanitized, or maybe the operators themselves are putting in wrong values. So what your program needs to do is detect errors where possible, and then rather than crash or stop responding, it should do something useful. So first thing you can do is sanitize inputs. For example, if you're asking for someone's age, you might say, the age needs to be between 0 and maybe 115, or maybe a bit higher. I don't know how old people will live in future, but 115 will probably be a good one for now. Maybe if you do get an error outside that, you might say, if someone is living to 116 years old, you might throw up a dialogue that says, 116, are you sure? And at least get the user to validate in case they mistyped. Maybe they meant 11 or 16. So yeah, very good to sanitize your inputs. Another thing to do is provide meaningful error messages to users. So you might say, for example, if someone tries to enter an age of 130, you might say age too high, and again, get them the option to re-enter that. Or maybe if there was an error later, because someone did enter an age of 130 earlier, you might have that error then as a result later that say this age cannot be handled or something. Or yeah, another thing to do is as well is store errors in a log file so that the developers can understand what went wrong, and also for help desks. As your application grows, it's unlikely there's going to be one person maintaining it. There might be a help desk that needs to be involved. So if your program crashes because the network isn't available, it would be a good idea to put that error in a log file so that the user might see an error message on the screen that says database not available, but then they might just close that dialog and walk away. But when your developers want to find out what goes on, you've also got that same error in the log file, and the log file could include additional information. So it might say what network resource isn't available. It might say, how many times you retried before it failed. And so again, there's different levels of error handling depending on who the intended target is. So you want meaningful error messages to users, but you might want more detailed error logs for developers and help desks. Now, when you're developing your application, again, maybe the MVP, you don't care so much, but later you're going to be reviewing your code. That can help prevent errors. And depending on how complex your code is, you can also do static and dynamic analysis along with extensive testing. So for example, you can test, what does your application do if you enter an age of 130? Can it actually handle that? Or do you get an error further down the line when you try and store that 130 in a single byte consisting only of 7 bits, in which case you will exceed the available storage? And then what happens then? So if you try and put 130 into a 7-bit byte, which can only hold a maximum value of 127, does it actually put in 127? Does it truncate it to 3? Does it put some other value in? So again, your testing to work out what happens is very important to find out how rugged and robust your code is, and error handling can help you understand where things go wrong. Another concept we come across is algorithms. An algorithm is a routine or piece of code that will take data, perform calculations, and achieve a result. Typical algorithms include sorting and indexing of data. That's important so you can more quickly retrieve data in future. Mathematical calculations, for example, averaging or linearizing a set of data. Financial calculations, such as, for example, calculating compound interest over a number of years. Finding the shortest path or the most efficient path. For example, that might include motion control, but also things like sat-nav and delivery type applications. We have advanced analytics, for example, digital twins and physical models of equipment. There might be machine, process or fleet optimization. Cryptography, this uses some quite complex algorithms. And then you get machine learning or ML and AI type applications, which are also examples of algorithms. Other algorithms might include things like social media. So when you're looking at social media, you have a feed, the algorithm puts up something that you might want to see next. So again, that's another example of an algorithm where the computer is deciding for you on the basis of past preferences and also other influences. Maybe, for example, an advertiser has paid a particular amount to target people like you, and the advertiser that pays the most appears most often in your feed. So that's another example of an algorithm that you might come across on a daily basis. Now, algorithms can be simple. For example, with averaging, you just add up every value and then divide by the number of values. But they can also be quite complex. So for example, what you might want to do is calculate the results for every possibility of a particular matrix or a set of decisions that might occur using some sort of recursion. You might then assign a weight to each result, and then based on your criteria, you might choose the lowest or highest weighted result and use that one to act. For example, let's say you're playing chess against a computer. This is typically what the computer program does, is it's looking at a variety of results for every possibility of allowable moves. And depending how sophisticated your chess playing program is, it might then look at all the future moves as well, going all the way up to the end game, or maybe it's looking 2 moves ahead or 3 moves ahead or 10 moves ahead. Obviously, the more moves ahead you look and the more potential moves there are, the longer it takes. So there's a calculation here that has to take place within a certain time. But again, the more levels of recursion you can do, maybe the better the outcome from the algorithm is. So chess playing is a good example of how a complex decision-making algorithm might work. Look at all the different results, calculate what is the best and worst one using some sort of pointing-based system, and then you choose the lowest or highest weighted result based on, for example, with a chess program, that would be based on whether the computer wins or what the result, the best outcome might be. It might be shortest path to win, so it's not just that the computer wins, it might be that it wins as quickly as possible with the fewest number of moves. So it can be very complex with these advanced decision-making algorithms. Now, in the early days of writing code, and maybe even today for some simple applications, you can just write the entire code yourself. As applications get more complicated, what developers can do is they can create libraries of reusable code. So that code is things which you use quite frequently. So maybe, for example, like a print driver, there would be a single print driver which would be written by the manufacturer of the printer, and they would issue that as a piece of code. You don't necessarily get access to the source code, but you get access to all of the code that you would run, and you don't need that way to write your own print driver. Now, a lot of developers are releasing their code as libraries. They even release it as open source, in which case they don't get paid, but some developers are actually making this a business. By releasing code as a library and charging for that, that's a business model. And then what you can do within your platforms, you can include these libraries as well as provide options to import additional libraries. And there are also then application program interfaces that the developer can use to implement functions as well. The API might also refer to an external interface provided by a remote system. So the idea of these libraries and APIs, these extend the amount of work that a computer program can do without the developer themselves actually having to write that library or API. And from the development point of view as well, the person who's writing the library or the API, that could be their business model, or maybe it's something they offer to allow third parties to interface. And it's also something they might do as well to protect their intellectual property. Rather than give out the source code, they just give the libraries as object code or as a remote API, and that way they can protect all of their investment but still let people use what they've developed. Another aspect of early applications is the output was often very simple. If we go back to the original coding days, there might not even have been a terminal. The output might have been a punched card. Later we actually had terminals where the output was a line or more of text. These days we have more graphical devices. Now, in order to understand what the output of the application is, it may well be that we use one of these user interfaces. So this is typically for the user, as the name implies, and it's the interface that user uses to actually understand what the application is doing. And if it's a graphical user interface, then we call that a GUI, or graphical user interface. So this can include the screen or monitor to display results. It might be forms to allow data input, and that can also be extended even to the keyboard and mouse and the window arrangement on the screen. Could include the printer as well. With other applications, it might include things like head-up displays and maybe other forms of input device. So user interfaces can be very simple with just a keyboard and a line-by-line output, all the way up to very complicated applications. For example, if you're flying an airplane, you could configure the whole cockpit as the user interface. So there are dials, there are switches, there are buttons, there are gauges, there are screens. There's not one single interface. The whole system is that user interface. But in computer terms, typically we're talking about a screen, or these days it would normally be a graphical screen. Maybe it would be a web page, but usually there's some sort of interface to allow the user to operate the actual computer system and interact with the computer system itself. Now, modern applications often have to handle large amounts of data. These can be structured into a file, often associated with disk storage, but that could also be in memory or cloud-based. And we have a large amount of data in a file, then typically there would be a common format we use, such as comma separated variable or CSV file. Maybe we use extensible markup language or XML. There's also JavaScript object notation or JSON. And it might be we use a combination of those depending what we're trying to do. Programming languages can open, read and write those files, and a lot of common programming languages have extensions to handle those objects in the files in the above formats. So for example, you could open a comma separated variable file, you could read down all the different lines of data until you get to the line you want, and then you could read along that line and then find the actual variable within that line that's relevant to you. Same with XML. What you would do there is you would go down the application to find the relevant piece of XML data you want, and then use the different parts of the XML markup language to actually define what data you want, and the programming language can handle all of that for you without you having to write your own file handler. For larger and more complex data sets, I recommend using a relational database management system, so also known as RDB or RDBMS, and typically there you would be using the structured query language that we mentioned earlier. And again, I've got a whole other slide deck that covers SQL databases, and that can give you an idea about how we manage that. But what can happen is it's all very well using files, but as the application grows and grows and grows, you often end up with multiple files. There's links between the files, and if a single file got corrupted, that can corrupt everything. If you start off using an RDBMS, then that can eliminate all of that problems in future. However, you've also got the option that if you do that RDBMS work, you do require that extra database to begin with. Now, there are simple databases you can use. Again, check my other session, but SQLite might be something that's simple, or you might just decide to interface directly with a SQL Server database. But certainly that's an option for very large complex applications over one or more files. So here's how you would develop an application. Applications can be complicated. Certainly today they're often very complicated, and they might consist of many programs, as well as data definitions. There's also the definition of the user interface, and there's the definition of how you handle that data and how you manage the data. Typically what we do is, to develop an application, we use the waterfall method. So with the waterfall method, we're starting at the top, and then there is a defined process from top to bottom, and at the end we have the working program. Now, waterfall isn't ideal because it doesn't allow very well for recursion and changes in the definitions earlier on, but it is a well-known way of doing things. And the way it works is a defined set of steps which are typically executed in a defined order, and that order only. So we start off by defining what the user wants, and the output of that should be a user requirement specification, or URS. So that URS defines what the user wants. It doesn't attempt to say whether the program is feasible or not, although that's one thing that can come back and bite you later if you try and put something in the URS but can't be done because the application technology can't handle it. But generally, it's purely about what the user wants and not how it will be implemented. The next thing from that is we define a functional design specification that defines what the application will do based off the URS. Now, there's a problem here because it might be that we miss things from the user requirement specification, because each time you do this, there's a level of abstraction, but also it gets more complicated. The user RS might be a very simple document. The FDS might be a much, much bigger document. But one challenge here is, as we're going through these functions, what happens if something wasn't in the user requirement specification? Well, if it doesn't meet the FDS, then it won't get done. So you've got challenges of how well do you do each stage and how well do you actually implement it, and what happens if you miss steps. But anyway, in a perfect world, we have a perfect user requirement specification, from which we have a perfect functional design specification. From that, we create the software design specification, which is how the application will actually implement the functional design specification. And then what we do is, this is where we start defining code. We implement what's in the SDS, and then we'll release it. And then what we'll do is we'll test. Ideally, we're testing during development, so that's during phase 4, and also at the end. So you may need an additional document here, which is a test specification or test specifications. And then finally, you need to document the application, what you did in terms of the software design specification is how it was developed initially and how it was actually developed in the end. And then also there might be a manual for the user and so on. But this is the waterfall model, quite straightforward. You go from start to finish. You start off with what the user wants to do, and at the end of that you have an application that meets their requirements. As I say, not perfect, because you might miss steps. It might be that things can't be done. It might be that there are changes that come along afterwards. So there are definitely deficiencies here, but certainly this is the classic waterfall model that most applications are developed using. Now, the waterfall method is quite a high level way of doing things. There was that step 4 where we talked about developing the code. That's arguably the largest part, and it was almost a throwaway statement there. You develop the code. Okay, how do you develop the code? Well, this is where the software design specification comes in, and this will try and tell you how to actually implement the code. So there might be flowcharts. Flowcharts are graphical images showing how an application or algorithm might execute. You also might write pseudocode. Pseudocode is an informal natural language implementation of your application or algorithm that can later be converted into actual computer code. That's certainly a mechanism I often write. If you're thinking about how will I implement an algorithm, you start off with pseudocode, and you can have start, define data, test data for a particular step. If data is something, then continue, else perform an operation, and then loop round until all the data is handled. That would be a very simple sort of pseudocode to handle an algorithm, which you could then convert into Python or C, C++, or whatever your application is. Now, it's also possible for the developers to describe what triggers a condition and what happens within a loop without considering detailed implementation, including variables, values, and arguments. Again, that might be pseudocode, or it might just be thinking in their head. But those flowcharts and pseudocode, they are very helpful for developers to understand what is required and to reduce the overall development time. And also, those flowcharts and pseudocode can also be used as the documentation for later on. The actual final code might be very complicated to understand, but a flowchart and or pseudocode could certainly help you understand what that application code is doing. So a great step as an interim step between the software design specification or the functional design specification and what the actual code does. A great way of actually splitting it down and making it simpler. Another technique I was taught, this started as like a time management thing, but it was apologies to anyone who might be offended by this, but one of the original ideas was, how do you eat an elephant? And it comes down to one bite at a time. So what you do is, if you've got a very large task, you split up into smaller and smaller tasks until you've actually got each task implemented, and then you build and add all those tasks together until you get your final code. Again, flowcharts and pseudocode might be part of those smaller parts that help you develop and write the application. Now, this might be a separate document, or it might be inside your software design specification, but you also need to think about your data. You need to have a data definition. And this might be data that's used by the application, such as basic data types, might include allowable values. You might have more complex concepts like relationship between variables. And if you're defining any structures or arrays, you'd need to define those as well. And if you're using a database, then there might be a lot more work to define that data layer. So as well as all that basic data definition, you also need to define database tables, entity relationships, maybe primary keys and indexes and so on. But that data definition in a large application, that deserves a document by itself, as well as the software design specification, or certainly that would be a big index or appendices as part of that data definition for the software design specification. Again, this also forms your documentation for later as well. So it's not just something you develop as you're developing the code. Having that data definition can be a very important part of your documentation for later modification and maintenance of that code. Now, assuming you've developed your code, you now need to do some testing. My recommendation is that you should test as you go along, and developers often do this. They'll do their own simple tests to make sure that the code does what they think it should do. But there also needs to be more comprehensive testing as well. So testing is required to ensure the code meets the application's requirements. There's typically unit testing for each module. This should be like your first formal test, and this is beyond what the developer does when they're actually writing their application. Yes, if you're developing an application, you might run it a few times and just put in some dummy values and just check that the output you get makes sense. A unit test is a more defined test to define and test that the module actually does exactly what it should do. So that could include upper and lower boundary limits. It might include error values or invalid values to test for error handling. And of course, it would include a variety of expected values to test that the module actually functions under normal circumstances. You then do integration testing. This tests the interfaces between each module and for groups of modules. So for example, you might have a high level unit test for one module, and then there would also be that module that calls other modules. So your unit testing for that higher level testing would include what those interfaces might use. So again, the testing here, depending on how clever your application can be quite detailed. You then need system testing for the overall application. And this is where you might also need some users who are testing the application, and you might give them examples of what to do, or you might just let them try and play with the system to see if they can break it. So different levels of system testing that also need to be tested to make sure the overall application works. Testing shouldn't just include correct inputs, it should also include injection of incorrect inputs. And also, particularly, you should test around the boundaries. So for example, if your application says that a person's age can be between 0 and 115, what happens if you actually put 0 in? What happens if you put 115 in? What happens if you put 116 in? So those need boundary testing as well as random values, like you might choose 40, 50, 35, 27, and you might choose some crazy numbers as well, -12, 158, 2000. So you've got to have a variety of tests against those, both including good inputs and bad inputs. What you also need to think about is regression testing. If you found an error in the code that something didn't work, then make sure you include that test for future tests. Maybe there was just one particular bug that you found, you fix that bug, great. But regression testing, make sure that bug doesn't get reintroduced. So if you did find a specific issue, maybe there's an error when someone's age is exactly 100, it causes a specific error, but you fix that bug, but you should now make sure you test for 100 for every new version of application. Maybe someone introduces an old library by mistake, maybe someone pulls an old version from the repository, maybe someone just looks at the application and decides, I'm going to recreate that algorithm, and they recreate it in the same way that the original error occurred. So again, you're doing that regression testing to make sure that an update that comes along later does not break the system is a good thing to do. And I have had occasions in the past where regression testing wasn't performed. Version 1 of a program might have some bugs. You fix those bugs in version 2. Version 3 comes out and some of those bugs come back for a variety of different reasons. So again, regression testing makes sure that you test existing errors to make sure they don't come back. One thing to note is complete testing is not possible, and there's no way that testing cannot find every possible error. The more tests you use, then that reduces time and risk, but no software is ever going to be 100% bug-free, partly because it's impossible because of the complexity of modern applications, also because bugs might exist in underlying libraries and so on, but also because it's just not possible to test every single input. Now, I had an example of this a long time ago. Someone said for a system, we've got 100 inputs, we should test every combination of 100 inputs to make sure that the system doesn't fall over in a dangerous state. Yep, great idea. Okay, so we'll start off by testing all the 100 inputs at 0. Then we'll put the first input on. Then we'll put the second input on. Then we'll put the first and second input on. When you calculate that out, there are actually something like 2 to the power 10 different inputs. It's actually more than that. There's a huge number of inputs. And if you could do every test, say 1 test every second, you might find that the testing takes you 1,000 years. And that's only for 100 inputs, where it's quite well defined in terms of what the inputs are. As soon as you get to an open-ended system, where you've got a lot more inputs and a lot more underlying different variables, then it's just impossible to test everything. So, people who say we have to test everything, it's just not possible. There will always be bugs. Those bugs may never occur. Hopefully they won't, but there are always bugs, and there's also the possibility of bugs arising in future because of external influences. Maybe, for example, someone runs an old application on a new version of Windows. It might be that the way the new version of Windows handles something is different from an old version. So you should try and think about what might happen in future, and you might want to test for that. Or you might just say this programmer only works under these specific set of conditions. So a lot of things you can do, but you should certainly test, but just bear in mind you can't test at everything. Now, we mentioned that error testing is often neglected, so is documentation. I've used a lot of computer code that has minimal documentation, and that's not helpful to the user. So ideally, what you should include is a variety of different documentation levels. For the user, they need user manuals and help files. They also need to be kept up to date, but that means that's a major task. But that's just for the users. You've also got all of the people who develop the code and maintain it. They also need documentation. So there's documentation inside the code itself, including meaningful variable names and well-structured comments and well-structured code in the first place. You might have specifications and style guides which define how the code should be written, so that users from the same organization have a lower learning curve than if they're looking at it for a new application. You might also need revision tracking and change logs, so there could be lots and lots of different types of documentation. Even if it's just you writing code, and I've been here before, you can write code, it works perfectly, you think, yep, it's all documented, I've got comments, the variable names are meaningful. You come back to it 6 months later, you've got no idea what the code is doing because you've forgotten. So even well-documented code, it's not enough. You need other documents to explain how it works. Again, there's that pseudocode, the flowcharts, maybe high-level descriptions, but also other things you might need as well, just to help you understand and realize what that code is doing. And that's for your own code. Imagine you're coming along maintaining someone else's code. It's that much harder. So there's no real limit to the amount of documentation you can have. But of course, the more documentation you have, the more time and money it takes. And whenever something is updated, that documentation needs to be updated as well. Something I found very frustrating is documentation that talks about a particular function, and when you go and look at that function, it's not there because it was deleted in an older version. So, and then you go to find the new version, and that doesn't have any documentation. So again, no limit to what you can have, but it does take time and money. In the past, applications could be very simple, but for a long time, and particularly today, modern computer applications are very large and generally beyond the scope of a single developer. So often, projects are developed as a team with multiple team members. Now, in order to manage a team, you need some sort of project management framework. So a project management framework that manages the project, manages the team members, and it makes sure that the objectives are achieved in the required time and for the required cost. So typically there's a product owner or a product manager. They define what the application should do. A project manager runs the project. Developers create the code. Testers test the code. And there may be others involved as well. For example, people for documentation. And teams can be huge. For example, for a modern computer game, the teams could number in the hundreds. But even for any reasonable size application, you could be looking at 5-10 people, and it's very rare for there just to be a single person who's developing code now, unless it's maybe some sort of open source component that would be used in a larger application, which is maintained by a single person or even developed originally by a single person. But that today is pretty rare. So you have to imagine that it won't just be you working on the project, there will be other people as well. So the project manager may just use that waterfall development model that we mentioned earlier. Traditional method, but very rigid. Define the URS, create the FDS, create the SDS, implement what's in the SDS and release. With, of course, testing and documentation. As I mentioned, quite challenging because how do you deal with changes? How do you deal with issues that maybe the URS doesn't meet what the user requires? How do you manage that you can't do what you want to do after it's been requested you do it? And often, this is a particular problem with software development, you often don't know how long something is going to take. So a waterfall development model might say, we'll allow 2 weeks for the URS, 2 weeks for the FDS, 2 weeks for the SDS, 12 weeks to implement, 2 weeks for testing. But what happens if the implementation stage takes 16 weeks? So, managing in this way is very difficult. And if there are changes, what happens if you get to the testing stage, the user says, oh no, that's not what I wanted? Do you go back to stage one and start again? Do you implement changes? And then actually a lot of projects, changes and change management is probably one of the most difficult parts. But certainly the waterfall development model, this is often the basic framework where people start. But do bear in mind it has a lot of issues with it. So we do have some other models as well that we can use. Now, rapid application development, or RAD, this was one of the methods that was introduced to overcome issues with the waterfall method. As we mentioned, changing user specifications, long development time, uncertain development time. So what the rapid application development steps do is it starts off with a very different way of determining what's needed. So first of all, we still have the basics of what the user wants. What we do is we have a list of user requirements, and that is used to create a backlog. The backlog will continue to be added to during the project, but the backlog gives you the list of things that the user actually needs. What you then do is you start developing the application to achieve this minimum viable product, the MVP, that we mentioned before. And what the MVP contains is the most important backlog features. So for example, if you've got an application which is to say managing maintenance, then you might start with the basics, which are the user management, the task management, and the task completion, and then maybe that's it. And then maybe in the future, there will be additional features such as user groups. There might be additional requirements around adding in documentation. There might be additional ideas of ongoing maintenance, continuous maintenance versus prescribed maintenance and timed maintenance. There might be a lot of features you could add there, but the minimum is just for users and the actual maintenance tasks themselves. So what you do is you release that initial MVP version with that minimal feature set, and then you seek feedback. If the MVP doesn't meet requirements, you start again. Maybe the way you're handling users is wrong. So what you could do is you go back to step one, you still have your initial backlog, but you might update or modify that backlog, and then you would develop or redevelop the application or parts of the application which don't work. So that's a so-called pivot. If the MVP does do what you need, then you continue development and release based on the backlog. Now there are some downsides with this. The downside is you've now got an open-ended project. How do you define when the project is finished? Because effectively it isn't. Although you could argue with a lot of software applications, they are never finished. There are always going to be changes of some sort. Another argument here is that as the application grows, you're very much constrained in the future by what you did to begin with. So for example, maybe you decided right at the start you were going to accommodate a particular number of users, and you chose an underlying structure based on that number of users. You might later find actually you need more users. So that might mean that when you go back, you have to completely rewrite parts of the application, because although they achieve the MVP, they don't achieve what you actually need for the final part or the final version or an interim version or whatever. So the rapid application development also has its issues. Another aspect is, how do you define what the MVP is? What's important to one person might not be important to another, and vice versa. How do you define what goes into the backlog? Once you've got the backlog, how do you define what feature set to work on next? Again, one stakeholder might think that one thing is important, another stakeholder might decide something else. And it is possible with the MVP to meet the requirements of one stakeholder, but be completely useless for other stakeholders. So then you're into the position of who has the most power as a stakeholder, and just because they have that power doesn't mean the application will meet the requirements of the majority of the users. So not perfect, but can be an improvement. And it is possible to combine waterfall and rapid application development as well. You can almost say we'll do a waterfall mechanism, but we'll loop with inside the waterfall mechanism, use this rapid application development approach. Now, Scrum is another example. Scrum is a form of rapid application development which uses an iterative and incremental framework for product development. The idea is you have a set of goals, so this is almost your backlog if you like, and you break the work into those goals and give them to teams. And what the idea then is you give each team a specific time, typically 2 weeks, but no longer than 1 month, and that team has to complete those goals within that specified time or within that sprint. Now, during the sprint, the team works on the goal to be completed, and you assess progress in short daily stand-up meetings of 15 minutes, typically called a daily scrum. And at the end of the sprint, the team holds further meetings. There will be a sprint review to demonstrate the work and solicit feedback, and there will be an internal sprint retrospective. So this is a good thing in terms of you now break the work into achievable goals. So those are like your objectives or your backlog, if you like. But the downside is, if you're working for 2 weeks, how do you know that your goal can be achieved within that 2 weeks? You might find you get to the end of the 2 weeks and that 2 weeks doesn't work because you haven't had enough time or you haven't understood the requirements. So this isn't perfect either, but this is the way a lot of projects are developed these days. It does make sure that within a defined period of time, you do meet particular objectives based on those sprints. However, this can be very hard on the people who are writing the software. If they know they've got 2 weeks to write something, you might have to cram in a month of work into 2 weeks. So you might be doing very long hours. That can mean that shortcuts have to be taken. You might eliminate some testing, which can end up in a less reliable project in the future. You might skip on documentation. So there may be a lot of issues with having these combined sprints or these defined sprints where you don't necessarily do everything that needs to be done in order to have something that meets the final requirements. And you still have the problem of how do you define those requirements? Again, you've got your objective or your goal. Who defines that? So one stakeholder thinks is important, maybe another one doesn't. But this is a common methodology, and again, it can be combined with the waterfall mechanism to some ways. But we do find this being used for larger teams. And the good news is, it does give you defined goals within defined periods. But the downside is, it can be very hard on the actual people doing the work. Now, here's an example of developing an application. Think of a computer game. So this would apply to other applications as well. But what you've got with computer games, you've got a particular process here. Remember, there could be several hundred people involved. Certainly a large marketing team, they would be used to define the target market. You then define the outline of the game. That could be itself a minimum viable product in itself, such as a demo or a playable or walkable type outline of what the game should do. Certainly there's a lot of graphics development to be done. You've got both 2D or 3D, as well as all the gameplay that goes on. You then need to choose a platform for development if you haven't already defined one earlier on. So that could be something like Unity or something. And then you've got all of the assets to develop. So in this case, you've got a lot of people involved. You've got people who are actually doing the code, people who are designing the levels, people who are actually drawing the assets such as textures, people defining the characters, voice actors. And of course, there's still some coding in there because you still have to handle aspects of the game that may not be available in the platform. So there is often some coding. And there's a huge amount of testing. You often find that every level within a computer game, you might have 30 levels. Every one of those is tested by multiple people before it's released. And even after release, there are still problems. So you need a team that has ongoing development. So computer game development is a very interesting aspect of computers and coding. And it is a large market. If you think about computer games, the market for computer games is probably bigger than the market for films that you would go and see at the cinema. So it's a huge market, and again, very good example of how computer applications are written with very big teams, lots of developers, and lots of project management, as well as the marketing side, of course, which is also very important. Now, something I've not touched on so far, cybersecurity. Applications have to be secure. Even a simple application running on a single computer, you need to be careful that you keep the data secure and the application needs to be secure. And there's all these ideas about protecting the data. So you might have usernames and passwords. You might have to be careful how you store the data. There might need to be various levels of encryption. So cybersecurity, in order to keep an application secure, must be considered from the start. This isn't something you could add on afterwards, although you might have to if it's a legacy application, but generally you would use a secure development process to make sure that cybersecurity is built in from the start. So there's lots of questions. What platform and external code or libraries will be used? Each platform must be secure, the external code and the libraries must be checked for security. How will users be handled? How will data be handled? Again, if you've got data coming from outside the application, particularly if you've got data coming across a network, you've got issues there. If you've got a large distributed application, how will the nodes communicate and how will the data be protected? How will the application and any updates be deployed? And then you've got various different testing. So on top of testing the application, you now need to do testing for security issues. So there's both white hat testing, which is people who are testing to make sure that the security works as it should do. But you also have red hat testing, which is people who deliberately try and hack into the system and break the security so they can get access to the data or somehow subvert the operation of the system. You also need to think about additional logging. You need to log all the user interactions. And depending on what the actual framework you're working under, these days it's more and more important to have a reporting system. So if there are any issues, that reporting system alerts external parties and they can in turn inform you as a developer, but also inform users so they can take appropriate action as well. So cybersecurity is getting much more important. Again, needs to be built in, but also you need to do a lot of action within the actual code development in order to make your application secure. So you've developed your initial application. It does what it's supposed to do, but it's slow. This is often the case. Initial code can run slowly, and what you often have to do is optimize that code to make it perform faster and improve performance. So there are several techniques to this. The key one is finding bottlenecks and eliminate them. So maybe you're running on a platform that's too slow. Maybe you have to increase the size of the platform. Maybe it needs a faster CPU or more memory or a better operating system that runs faster. A lot of the time in initial testing, there might be test code which you can remove. It might be you're using an algorithm, and this is a complete subject in itself. An algorithm you're using, it might be that there are better, faster algorithms depending on what you're trying to do, but also how the application is being used. There could be two equivalent algorithms. One works better under some circumstances and one works better under others. And you might not find out until you actually start to find out how your code is being used as to which one is better. You might want to refactor your code to make it more efficient. Refactoring, particularly if you're using things like rapid application development or the Scrum type mechanism, this is where you come back later in the code development cycle and you effectively rewrite your code. So part of that is including faster algorithms, but it might also be tidying up data structures. It might be completely rewriting the way the routines work. It might be splitting up more routines into smaller routines, or maybe combining smaller routines into bigger routines. It might involve a lot of testing. Again, that's where this static and dynamic analysis can come in. So there's a lot of work you can do there to optimize and make the code more efficient. There may also be platform optimization tools. For example, databases. A key with databases, they need to be correctly indexed. Too much indexing slows them down. Not enough indexing slows them down. So there are database indexing tools you can use which are not related to what your code does, but which are related to the platform you're running on. And as I mentioned, time helps. As computers get faster and networks get faster, upgrading the computer hardware and networks can help as well. Now, if you've got a small application and you're a developer, you might write it, issue it, and that's it, job done. But most code and especially if you've got a large application, is going to need some sort of maintenance. First of all, user requirements change or are added, bugs are found and need to be fixed, the platforms evolve, and also from a marketing point of view, a refresh perhaps of the user interface may help find new users, or again, this could come back to the user requirements. New requirements could open it up to a wider user base. So it might be a marketing reason you're doing maintenance, not just something to do with the code itself. So you need to factor in maintenance and updates into the project costs. They can be charged for with a maintenance contract, so it may be that they're actually a revenue source in themselves, but it may be you also need to give those updates free of charge. So that's something else you need to think about is, what is the mechanism for performing the updates, but also how are you actually going to monetize that, and can you monetize it? Maybe you can't. So there are practical and commercial impacts to maintenance, not just the actual fact of fixing the bugs. So typically the developer will decide when and how to offer upgrades. Maybe you only have a major issue and update that way. That's often required to fix major bugs and cybersecurity issues. Maybe you go once per year, but these days, if you do find a major bug or a cybersecurity issue, you probably can't wait a year. Maybe if there's no other issues, then it's just when there's a significant change required. So maybe the operating system or the platform becomes obsolete. For example, your Windows 10 has just gone obsolete, so maybe you need to update to run on Windows 11. Maybe there's a merger or an acquisition of your business. That could be as little as every 5 to 10 years or so, but it may be that you have to have frequent updates. Typically these days, if you look at the Microsoft cycle, they've gone to like half-yearly type releases. But although the half-yearly refers to the product, often the actual release itself is only an annual release, or maybe less, but typically it's an annual release. But within that year, there might be multiple bug fixes and updates for the subsections of the updates. So there is something with Microsoft, for example, there's so-called Patch Tuesday, and I think that's one of the Tuesdays in the month where Microsoft issue the bug fixes for their major issues. But if it's a major issue, they might have to release a bug fix before then. So it's a pretty complicated subject, and it might depend as well on the commercial aspects. Who is your customer? How are they paying for the software? What sort of service level agreement do they want? So there's a lot of aspects to be considered when you're maintaining the code beyond the actual just the coding aspect itself. Now we've talked about refactoring code. As applications evolve, or even from the start, inefficiencies can be developed. It depends how you develop your code, but this often happens as a result of maintenance. Software can be in use for multiple years. For example, where I used to work, we've got software that was introduced in the 1990s, and it's still the current platform today. It's evolved over something like 30 years. What can happen there is each time you add a new feature, the existing features are still there and may stay as they are. New features then can involve using new bits of code or maybe trying to leverage the old bits of code. But over time, inefficiencies can develop. There may be overlapping bits of code, there may be duplication, there may be redundancies. And this is what refactoring aims to do. Refactoring aims to remove those inefficiencies, to improve performance, and also to allow ongoing maintenance to be easier. There's a big challenge though with refactoring code. It can be very time consuming and it can be very risky. So the first thing you might want to do is look through the code and remove old routines that are no longer used. But you might not know what the old code is. A routine might only be used in a certain set of circumstances that you don't test for or don't know how to test for. You might remove unused variables, but find that actually that variable is used for some other reason. It might be field lengths can be changed, but those field lengths might have some sort of impact on something else that's going on. Other things involving, if you're using object type programming, making sure you close objects and files when they're no longer required. Otherwise that can remove or cause memory leaks. Memory leaks can end up using more memory than the program has available, and that can end up crashing a system as well. If you've got very complex looking code, a good idea is to rewrite it to make it easier to understand. But again, that's very open-ended, very time consuming. And you've also got to retest, because if you've rewritten your code, okay, now it looks better. How can you be sure it still does what it's supposed to do? So there's a lot of testing involved. Choosing faster algorithms, we mentioned that. Again, there may be algorithms you chose initially because they made sense then, but now they don't make sense because the way the application is being used is different. Maybe you've got larger databases with different algorithms. Maybe the data is already optimized and you can use an algorithm which is better suited to the optimized data. There's lots of aspects there. Again, as I said, that's almost a subject in itself. And also there may be platform updates. So for example, .NET, Microsoft applications written on .NET. .NET has a new release about every year. So over the years, you probably have to rewrite to use a new version of .NET. That will help from a cybersecurity point of view. It will also help from a performance point of view, because generally each version of .NET is a bit better. But again, it's more risk, there's more work required. You may have to rewrite functions which are no longer available. So it's hard work. And again, then there's also that option of using these static and dynamic analyzers to find issues. The legal aspect of software is protecting your intellectual property. So the way we do this is with software licenses. First of all, a developer who writes code owns the copyright for that code. And all you need to do that is include like copyright, developer name and year in the comments. And then that means you own that code. Obviously you need to keep a backup with that copyright in. You probably want to include that copyright somewhere in the installation mechanism, maybe somewhere else in the software, but that should protect you. Now in the US you can patent software, but in the UK or Europe that's not allowed. So that copyright is your main protection mechanism. Now the next thing you can have is a software license. This allows the developer, that's you, to distribute your code with a set of rules that define what other third parties can do with that code and what warranties apply. Without a license, or by not following the license, use of the code by a third party is effectively theft. So what they have to do is they have to agree to that license, and you can define what they're allowed to do with that. If you've got an open source project, then licenses like the GNU public license or Creative Commons licenses could be used. But if it's a commercial project, then the organization should develop their own license. Liability can be an issue, so it's definitely worth consulting a lawyer to understand what sort of license you have. And what you'll often see in a license is there are very limited liabilities and also limits of time. So licenses can also define how long the software is maintained for. It can certainly define what happens if something goes wrong. And also it also attributes ownership, and it may include details like where the law should be applied in order for any trials or whatever to be performed. Notice that whatever you put in the license, that may be overruled commercially or by outstanding laws or legislation in a particular country. So again, consult a lawyer if you're not sure what you should be doing there. Now we mentioned open source there. Open source software and libraries are published under licenses that allow for free use. So generally that means that you can take that software and use it with no charge back to the original developers. However, there may be restrictions on modifying the code. There may be restrictions that you have to attribute to the original user. And there may also be restrictions around personal versus commercial use. So if you are using an open source software, check carefully what you're allowed to do with it. And also check carefully what you do when you actually reissue that software. Now, source code should be available for open source code to make sure that it's secure, so that allows independent verification. And it also provides access to a community to make changes and fix bugs. But ultimately, the key issue with open source software is if you use open source software, you're the one that's liable and you have to determine its suitability for a project. So this is where proprietary software comes in. Proprietary software and libraries are published under more restrictive licenses and often cost money. You rarely get the source code, but the great thing about proprietary software and libraries is there's a vendor who can provide a warranty and consultancy for the use of code. And I've not written it down here, but there's also someone to sue if it goes wrong. With open source, effectively, it's use at your own risk. Proprietary software may say that as well. But with open source software, if you haven't paid anyone and the license specifically pays or says there are no warranties, that's very different from a restrictive proprietary software license where you bought it from a vendor and you've got someone to go after if anything goes wrong. So a lot of people say that open source is best because it's free, but actually I do find a lot of organizations don't like open source or free software. They would rather pay someone for proprietary software, precisely because of that liability issue. Now, we talked about users. Users are arguably the most important part of software development, but they're not often considered as part of the actual software development process, other than maybe that user requirement specification. But you really need to consider who is the user for your application. I mean, there's multiple reasons why you might develop code. Maybe you're developing for fun, maybe it's an open source project, maybe you're reselling that software, maybe it's an internal application in an organization, maybe it's software as part of a larger application. Defining who that user is and what their requirements are can considerably change the way the application is developed. And one of the ways we can do this is we think about different personas. So rather than try and think, who is the user, you could give the user a name and like a day-to-day role. For example, you might have administrators, supervisors, day-to-day end users, people who provide technical support, day-to-day maintenance and so on. And then what you could do is you could consider those personas and see how their requirements are met as a way of making sure that your software covers as wide a user base as possible. Another aspect is thinking about systems. Now, often when people are writing code, they're thinking about their individual lines of software they're going to write. But in application development, it's very rare that you'll be targeting a single system. There will be multiple systems. So we have soft systems, and I just mentioned users on the previous slide. Users are a system or a part of the system that are very soft. It's very hard to define a particular user. We might have an admin. What does the admin mean? What do they do? It's a so-called soft system because it's around people and things which may change. Development teams are the same. How do they work? They are soft systems with various different ways of working. Project development methodologies, they're also soft systems. But then we also have hard systems. So the computer hardware is a hard system, and the computer network, that's another example of a hard system. But we don't have a single system in the application development. There are multiple systems. We're combining both soft and hard systems, as well as other systems. The operating system can be considered as a system. A database can be considered as a system. The application development platform can be considered a system. So what you can do is, if you adopt systems thinking, this can help understand the different systems and how they interact. And it helps make sense of complexity by looking all of the holes as well as the relationships and splitting them down into smaller parts, but also thinking of it as a whole as well. So you can use a variety of different techniques. You can use English language or natural language descriptions. You can use a variety of diagrams. You can use entity relationships and so on. There's lots of different ways you can understand systems. And from systems, there's no real right or wrong answer, although maybe for hard systems, it's a bit more defined. But for many of these aspects of systems, it's all about understanding. And the more understanding you've got, the better your solution can be, because you've got a wider understanding and a better understanding of what needs to be done and how the system, the final application will work. Now, because modern code is so complicated, we often use some sort of code management tool, also known as software configuration management. Small projects, it's quite easy to have your code managed manually, but most projects will use some sort of developer platform or version control system to create, store, manage and share code. For example, Git or GitHub, which can be used for open source software. And what this does is this allows multiple software versions to be managed as well. So you could have the branch, which is used for the main version, and that's where you'll have any bug fixes as well. And the main version or the branch, that's what you use to issue to your users. The trunk is where you start by then merging off different branches and adding new features. And then the idea of having trunks is they can be merged back into the main branch once you've satisfied them. But trunks can also go off to be their own application as well. So you might have a fork or a trunk or a branch goes off, and from that way, your single base application might end up being several different applications. But equally, you might want to merge all of those back together again, because you might want a single set of code rather than multiple different applications you have to manage in the future. So again, this is part of the project management and the project development methodology. You need to think about how are you going to manage your code in order to be able to have it working for multiple users. Do you have one set of code for everyone and maybe just switch functions on or off? Or do you have individual deployments, each of which only have their own code that they need for those requirements? And then again, if you find a bug that affects multiple applications, how do you merge those bug fixes back into all of the code? So there's a lot of considerations to be made here. One thing you can do as well is you can also things like take snapshots and have tags to refer to that snapshot in time, and that's how you can specify a particular version or release. So you might say, right, here's all my code, it has multiple different versions and builds, but this particular version, yeah, we released that, and that was version 5 of the software. So those code management tools also allow you to specify exactly what is released at a particular time and give it a version number, so that becomes part of the history and development of the product as well. Now, at the time of writing, there's a lot of talk about artificial intelligence and machine learning. I think of those as slightly different. A lot of people talk about artificial intelligence, and when they talk about code development, they're talking about large language models. So a large language model is a statistical model of what comes next. So what you can do is you can ask a question, and the large language model will be used to look at that question and then statistically determine what comes next. So if you think about a question like, what code do I need to solve XYZ problem? And the large language model will look at existing examples and it will give you the code that does that. It's not as simple as that, it's a lot more complicated and the answer might not be right. But that's large language models. Machine learning is another subset of artificial intelligence, which is more about an algorithm that uses a machine to sort of mimic what the human brain can do. And overall, if you consider AI is an algorithm that simulates the human brain in the computer system. We can't fully mimic a human brain. The human brain is too big and too complicated. But on the other hand, there are some AI algorithms that can exceed human performance in certain tasks. So particularly with machine learning, there are aspects of machine learning which can do pattern recognition, and they can recognize patterns far faster than a human can, but maybe with less accuracy. So often you still need a human in the loop to make the final decision. So very contentious subject, but also again, potentially a whole subject in itself. What we typically do with AI algorithms is we do this machine learning, and this is also how LLMs are programmed as well. We take a large data set, and by monitoring and analyzing large amounts of real-time and historical data, what we can do is we can come up with basic rules which we can use to build up that machine learning or that AI algorithm. So this is machine learning. And rather than programming, what you have is you have developers who curate a data set to be used, and then they have to monitor that algorithm for accuracy. A big challenge here is the actual algorithm itself is often opaque to human understanding. The algorithms are either so complex that no human can understand that, and they're also very large as well. And it can be very difficult to understand exactly what's going on. Hence, that's why you often need a human in the loop. But there are some algorithms which work quite well. So, for example, digital twins give you a model of what a particular process might be doing, and they can tell you if that process is going to go outside bounds by extrapolating much faster and better than a human can do. Some of this machine learning is also using statistical techniques like multiple variable data analysis, and they are more better understood, but even then the data sets can be very large, and the final results can be opaque or difficult for a human to understand. Now, cloud computing is a concept that comes off. It's not really related to programming. What the cloud really means is someone else's computer. It means you're using a remote server connected via a network. It's really the same as working locally, except you don't own the computer. The application is running on and the data is stored on that remote server, and you don't necessarily know where that remote server is. It's in the cloud. That's what the cloud means. It's someone else's computer running in a data center somewhere. And one of the key benefits of cloud computing is rather than you have to buy the computer and software up front, you pay per use. So in financial terms, this means moving the operational expenditure rather than capital expenditure. So it might be, for example, instead of paying several $1,000s or euros or pounds for a computer now, you can rent that computer at a few pounds or dollars or euros per day. Now, as your programs scale up, another benefit is that you can use more computers. Yes, it will cost you more, but you don't have to buy those. The cloud application can automatically scale up just by buying a bigger computer or more resources in the cloud. It can also give you more resilience. Yeah, there could be backups which are handled automatically by the cloud provider. It can give you better cybersecurity because the cloud people are generally better at doing that than yourself. And it can also cover system management, for example, backups and operating system updates. They can be outsourced to that cloud provider. Now, the downside is that yes, you're paying per use, but ultimately you may end up paying more than if you bought that server yourself. But for most people, that's not a problem because it's operational expenditure. The paying per use, the way you fund that is by you're selling your services and your software, and then that's used to pay, so it becomes part of the expenditure of what you're doing, and because of the scalability it reduces a lot of risk, and also maybe as your operations scale back, if maybe the software is used less than you thought, it means that you've not wasted money buying a bigger server than you needed. So lots of benefits. But equally, it is another aspect of management. You have to manage that relationship with your cloud server. And a big problem at the moment, although this will hopefully be fixed by upcoming legislation, a big problem at the moment is once you've chosen your cloud vendor, you're generally stuck with them. It's very hard to migrate your application and data to another cloud server. So once you've decided to go with, say, AWS, if you wanted to switch to Azure, that's going to be hard work. Yeah, it can be done, but effectively you've got to make backups of all your applications, download them from the cloud, download all your data, upload it to your new cloud provider, and there's going to be several hours or days of downtime while you do that. So something to think about also is how big are you going to scale? Because if you're going to scale a lot, you've really got to choose that right cloud vendor to begin with, otherwise you could be stuck in future. So we haven't actually mentioned how to do programming here, but this is a tough one because I'm of the view that you're either a programmer or you're not. And it's all very well learning about programming, but generally in order to learn about programming, you have to have that innate skill itself. There are a lot of people who believe you can be taught to program, and that may be correct. But then another level is just that level of abstraction and those brain structures you need. My view is that either you've got those or you haven't. And the older you get, the harder it is to develop and have those brain structures. But it may be that even anybody can do a simple programming exercise, but the really good programmers, I think they're born into it. And there's probably a good percentage of people who are programmers and capable of being programmers, but there's probably a good percentage of people who just won't understand and won't be able to get it. So how to start programming? Well, the first thing is look online and find online tutorials. There are actually websites where you can go and you can read about how to program, and they include interactive environments where you can also program inside that environment without installing any software. And these are often free of charge as well. Now, they won't let you develop a full application, but they'll certainly give you an appreciation of the syntax and the structure of the application and allow you to start writing. Once you've gone through a few online tutorials, you can then install a development environment on your own computer and you can start implementing simple applications. And then, of course, you'll develop skills by executing projects, because it's all very well understanding how an individual algorithm works or writing a simple program to do something, but ultimately the way to get programming skills is actually by doing programming. And one of the ways to do that is go out and find some projects to work on. Of course, you can always do formal qualifications. There are programming courses. Programming is taught at schools, and you can go on to college or university to study it there. And of course, you can get a job doing programming as well. And over time, the more applications you do, the better you'll get at those applications. Or maybe you'll be one of those people who realizes that developing computer applications isn't for you, and you'll go and do something else. So but certainly start programming online tutorials, and then maybe just play around on your own computer. And of course, if you've got the formal education and you've got through that, then you'll already be a programmer. So lots of ways to get started, but those online tutorials are the ones I would start with.